This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. In the last lecture we discussed about path of least impedance. So there are two things. One is a path of least resistance and another one is a path of least impedance or inductance. So these are the important concepts when you are designing your PCB, especially at high frequencies. Path of least resistance at low frequencies means DC current flows the path of least resistance, means this is your IC and then you have got a copper track. This is your PCB track. So you made a bend here, then it is coming, and then here it is coming. Here you got a resistance and then you got the ground, and the other part of this is connected to the ground plane. So this is the top plane. So then if the DC current is going from the IC and then it is going through the track and comes here, but the return path that will follow, the current follows the path of least resistance. See, because the return path will come from here to this point. But then you might ask, why the forward current, this current is not going like this? Because you already put the copper track like this. So if you are not defining your track, what will happen is, this is your track, so the current can only flow through this track. But the ground plane, why ground plane? The DC signal is coming from this to this point. Why? Because this will follow the path of least resistance. Then in the ground plane is a continuous. You know what I meant? It can choose any path. But then it is not choosing any path, but only this straight line path. That is the path of least resistance. And maybe I will, if you got confusion, see what it says is, so this is a PCB. So this is the PCB, so this is the top layer. So this is the top layer of the PCB. So PCB, then this is a bottom layer. So what it says is, if you got an IC here, IC, and then this is another IC here, IC2. On the top layer, this is your copper track. Maybe it is like this. So that the signal will be going like this. And then this is the DC. But then this is IC in the bottom. So you can see that this IC is here and then this IC is here. But in the bottom side, the return current, because this current is going, but then the return from IC2 to IC1, in the bottom plane, this is a continuous. You got everywhere the copper. So then it will flow from here to here directly. So that is a path of least resistance. Then another concept is path of least impedance or inductance. At high frequencies, when the frequency increases, current follows the path of least inductance. So means now what will happen is, you have got the ground plane, your signal is going through this copper track. So this is your track. but then the return current also will just follow the same, just under it. So this is the top layer, means it will confine under the track. See, it is confined under the track, so it is not a straight line. The straight line is the path of least resistance, but when the frequency increases, then it will confine under the track. So this is an important concept when you are designing PCB at high frequencies, because you have to always you have to keep in mind, even in your PCB design, you have to keep in mind how the return current is flowing. Otherwise you will get confused with the different planes. Once you are clear of how the return current is flowing, then you know how to design the ground plane. Even then you don't know any confusion, you don't have any confusion with your necktie. So this is an example, path of least impedance or inductance. Current flows So this is an example, path of least impedance. Current flows in the path of least resistance, and this is only true for DC currents. See, IC1, IC2 means if it is a DC, then what will happen is DC current will follow the path of least resistance. Current flows in the path of least impedance for AC signals. And suppose this is your IC1, this is your IC2. So on the top layer, this is a copper track. So this is your track connecting IC1 to IC2. Then some signal is flowing. Say some signal is flowing from, maybe I can say from IC1 to IC2, some AC signal is going. If the AC signal is going, what will happen is the AC signal return will be just below this one. See, the return will be there. But the DC current between this IC1 and IC2 will be flowing something like this. Path of least resistance. So another way of explaining is, we will come back to our diagram. Maybe this is I was thinking, how to present this one properly. So maybe this is a very good way of presenting. So you got your PCB, and then this is your IC1, this is your IC2. Then this is the top layer. So this is the top layer. Then this is your copper track. Then here, when you monitor the signal, so what you see is, on the oscilloscope, you put a 1 volt DC offset, and then you got some high frequency signals like this. You know what I mean? This is 0 volt, this is the time. So you made a DC offset of plus 1 volt, just an exaggerated offset. 1 volt offset, then you got very high frequency signals. Then what will happen is that signal will come. Then in the ground plane means this is below that one. In the ground plane, what will happen is the return current for this DC, that will be just underneath here. So return current for this DC, that will be like this. So this is for the DC, 1 volt. But then this return path is for, on the ground plane is for the high frequency. See, this is maybe a good way of explaining. So when you have DC and AC, the AC will follow the path of least impedance, means which is under the track. So that is the reason whenever you make a cut or some holes, you may make some holes if you have got through hole components, then the current has to bend it around this one. For example, this is an example. So you got here you got one IC. On the top plane, you got the copper track. That is a straight line that is coming from A to B. So that's a signal. So your signal is coming. But suppose you got a cut in the ground plane. So when you got a cut in the ground plane, what will happen? So if you got a cut in the ground plane, then the return path will take a, see, it has to bend and then come through this point. So you are creating some problem, because return current, if it is AC, the return current wants to be under this one, but then it is not possible because you are putting a cut. So then it will be going all the way around and then coming here. Again, here if you got another signal C to D, again it will be bending and then coming to this point. So that is not good, because then your signal your return current is undergoing. So what will happen? Because here, if it is just under the track, that is a path of least impedance. But then when it is taking a big loop, then your inductance is more, and then that can create some signal integrity issues. Then another aspect is when you have your PCB, the PCB on the top, see, maybe this is a PCB, yeah, maybe this is a PCB. On the PCB, what you see is on the top layer, you see the copper track, that is your signal. And then you got a material here that is called FR4, a dielectric material, FR4 for low frequencies. If you are designing high frequency boards in gigahertz, you will be using a material called Rogers, ROGERS, Rogers board. So you will mostly see FR4. Even for your DSO, you will be getting FR4 board. So then you see the copper track here, then you got the FR4, then you got the ground plane. Then the question is there any effect if you increase the dielectric thickness of your board? Why can't your board is this much thick? Why do you need very thin? Definitely these things will affect your signal. For example, on the top you got 3 conductors. So this is one track, this is a second track, this is a third track. So you got 3 track, 3 of them carrying high frequency signals. When 3 of them carrying high frequency signals on the top plane, and then this is your ground plane. So ground plane, here you got 3 lines, means 3 track carrying signals. On the ground, that is common, ground is connected together, ground is common. But then because this is high frequency, for this signal, the return path will be just below the signal. See here, under this conductor. For conductor 2, because this is high frequency, again it will be under it. For conductor 3, again it will be under. See, then what will happen is on the ground plane, you have overlap of currents. Current due to this one, current due to this one, current due to this one, because the return current. Because here there is no overlap, you don't find any issue because your current is flowing through this conductor, conductor 2, again conductor 3 in going in one direction. But the return path on the ground plane, that will be a little bit spreading. See, you can see the spread. And then you can see the overlap between the return currents. And then return plane current density for 3 closely spaced conductors. So if you place these 3 closely spaced, then the return currents can overlap. So when the return currents can overlap, what is the problem? In the ground plane, your return currents overlap. What is the problem? One return current may be 1 milliamps, but another one may be 2 milliamps, another one may be 3 milliamps. If you allow it to overlap, then your current is going to be at some point maybe 5 milliamps. If more current is there, what will happen is your copper ground plane got some impedance, copper got some impedance. Then your ground plane will not have the zero potential. Always there will be a little bit ground lifting. So that is an issue. If you find some ground lifting issue, then one of the reasons is this type of overlapping the current in the ground plane. And then this overlap you can reduce using the thickness of FR4 or by varying the separation between the conductors. See, return currents distribution. Current spreading in return path from microstrips of various heights. Microstrips is your copper strip, copper track. See, if your width is more, means if your FR4, if your thickness is 5 mils between ground plane and the signal, then you can see a big spread. But if it is little bit lower, then the spread is low. But if you are getting only 1 mil, see, and then for high frequency board, that is the reason you will find that is very thin. So that your return path, the return path current is just confined under this signal path. Then another concept you might be knowing is, so this one you might encounter when you are designing very high frequency boards. So you have to always keep in mind that you should have enough separation between the conductors, and also somebody might ask what is the effect of dielectric, the FR4 material or Rogers board material in your signal integrity. Then you can say that, oh no, that is very important, so you should be knowing this concept. Another concept you might encounter as a design engineer is called guard ring. So what do you mean by this guarding rings, pin guarding rings? So you might see in some data sheet, they will say that you have to use this guarding rings. Then if you are working in industry, then you should not think that, oh no, we never heard of this term. What is that guarding rings? So guarding rings means these are some rings around input terminals to minimize the effect of board leakage and capacitance by surrounding the input pins with the copper tracks at the same potential as the input. So it is nothing complicated. Suppose you are designing an operation amplifier. That operation amplifier is operating at like very, very small current. You are going to amplify it. Then there are some potential issues. So when you have an operation amplifier that is amplifying very, very small current, and then maybe it is operating at very high frequencies. If that is the case, your input terminals will create some issues. So issues means see the effect of board leakage. Board leakage means here you can see one pin. See, this is a pin number 3, maybe this pin number, maybe pin number 8, and this is pin number 1, 2, 3, 4, 5, 6, 7, 8. So then you can see that 2 and 3. So these are your input pins. So that is the reason this is the 2, this is the 3. And then, so there will be a board leakage. Board leakage means this pin here you are connecting your input, that might form some kind of capacitance with something nearby of low voltage. Then there will be a leakage, or at some point in the board. See, board leakage and capacitance surrounding the input pins. So then if you want to avoid that one, how can you avoid that one? So I can draw it and explain. So what it says is, so you have designed an operation amplifier, then that carries your application is amplifying very small current. So then this is pin number 2, and then this is pin number 3. This is just an example. So this I am going to ground it, and not grounding. So this is a pin number 3, and then this is a pin number 2. Then here I am going to connect some signal R1, R2, and then this is a pin number 4 is output, and then here you are going to connect some signal. So this is your application, but this current is very, very small, and then it is operating at very high frequencies. So when you make the layout, then what happens is maybe there could be some other track going here. That is one example, another PCB track, or you may have another capacitor here. See, another capacitor here, footprint, and then this is the ground. Then when your signal is going through this one, so this is at 0 volt, or here the signal level is maybe just exaggerated 1 volt. Then what will happen is there is a separation here. So this can form a capacitor. You know what I meant? And then when it is a capacitor, then the capacitor is will block DC, but then because this is high frequency, through this capacitance there could be some leakage, because capacitor will permit AC to pass through. Same will happen with even track. If this is 1 volt, this close by, this may be 0.5 volt, something is going on, then there is a potential difference between these two. So that also can form a track, or some point in the board here, and then that is also can create some leakage. Then in order to avoid that one, sometimes this is a real issue in some design. If it is very small current, then what you can do is how to avoid this one. So for that one, they will make a ring around it like this. They make a ring around it, and then they will bias this to 1 volt. So that this is 1 volt, this is 1 volt, so there is no leakage. You know what I meant? So you are preventing the formation of capacitance. So that is the reason when you look at this one, you may think how it is possible, but that is the reason you just see the layout. In the layout, you can see this is the input. So this is the 3 here, this is the 2 here. So it is surrounded by same potential. So if this is 1 volt, means that is shorting with your input voltage. So when this is some voltage, this is also same voltage, so that it is not forming this part with anywhere a capacitor. So that is called a guard ring. See, this is another example here. Guard ring. See, these inputs both are, they put another track around the input pins like this. Then you will be mounting the IC, so it will not short it, because this one is connected to your IC, this one is not connected to your IC, this part is anyway not connecting your IC because it's around it. And then will connect to the same voltage, same input voltage, and at the same potential as the input. So you have to connect to the same. So most of the time we can see that V equal to V1 means whatever the coming here, that will be connecting. See, this is an example. See, your input is going from there, they are taking a small part, they are tapping and then connecting to the guard ring. See, like this. So whatever, so if it is 1 volt here, around all this will be 1 volt. And then because this one got a negative feedback, when this is 1 volt, this also will be 1 volt. So that's the reason this is 1 volt, this will be 1 volt, and then the surrounding things will be 1 volt. So that is called guarding rings. So that is a concept of guarding rings. So you are putting some voltage, same voltage around it. Then split planes. We already discussed about the split planes in the last lecture, but then still we are going through again. So you can partially split your ground planes to help isolation noise currents in different sections of digital and analog circuitry. So in your case, you are completely splitting your two planes. In some application, you can partially split it. See here, this is analog, here this is a digital, and then this is the top, and then in the ground plane, they will split up to here, like this, and then partially split it, and then they connect the power supply here. But this is not very efficient. So partial splitting is not very good. So it's better to fully split the ground planes. And that's the reason in your DSO you will be fully splitting it. But then some people do like this. This also will be effective, maybe not as effective as fully isolating your ground planes. Then again, this concept we already discussed, split planes. The digital pins are, see, the digital pins. And they are basically, they will be creating lots of noise, which we already discussed. This is an analog ground plane, this is a digital ground plane. So the digital ground plane is creating a lot of noise. But then why we have taken ADC? Because ADC, when you got ADC, then you got digital and analog planes. Because even within ADC, then people will ask, okay, I got ADC, then before the ADC I got analog, and after the ADC I got digital. But then people will ask, where will you split it? But then you have to make sure that ADC, you can split with respect to the ADC actually in a very good design. Because this means within the ADC you got analog pin, within ADC you got digital plane. So if it is splitting very nicely, then it will be, somebody will be splitting like this. See, this is the analog part of the ADC, A0 analog, D10 digital part. So splitting will be through the ADC with respect to ADC. And then again, when you are routing also, you should be keeping in mind which way your signal is flowing. Like in the ADC, because this is a digital signal. If this is a digital signal, this is the problem with auto routing. So if you are using auto routing, what will happen is this part is digital, okay, and then this should be connecting to this point. Then in the auto routing, if that software is not very intelligent, it will take the signal track like this on the top. So this split is on the ground plane, the white split is on the ground plane. On the top, maybe your software will take the track from here on the top, the red one is on the top layer of the PCB, and then come here to this point. Then what will happen is the return current will be just under it because it's a high frequency. The return current yellow will come, then it will be under it, but then here there is a split plane. So it will take a round and then it will come, and the return current will all the way, it will come here, then it is a split, then it will come in under the ADC, come back, and then again under the top layer, and then come here. See, this is not a good way of routing. So better from here, take a line like this and connect it here. That is your track. So don't, if you got a, what it says is bad routing means because it's result in a digital trace in the analog area, which can therefore contaminate analog signals. See, so here what you are doing is because of this return current, so you are contaminating this analog plane because your copper track is on the analog, and then the return plane is mainly contaminating. So this is not a good design. So analog part you should be keeping in one side, digital part you should be keeping in another side. Then you can use only maybe a net tie. So that's what you do. The signal traces routed without crossing any ground cut. The return currents flow under the signal traces, minimizing the loop area because the only thing separating the signal traces from the ground plane is the thickness of the PCB itself. None of the currents wants to cross the ground plane cuts, which we don't want to do it. Then no currents are crossing the cuts, cuts are serving no purpose and thus can be eliminated. So what it says is sometimes, well, I haven't seen many, but sometimes what people do is when their design is simple, so they are designing a simple system where they have got maybe one sensor, one amplifier, then they go to ADC. From the ADC, they are storing their data. So in that case, maybe they will not split the plane. Instead of what they will do is, they will put, so this is a ADC, they will put only all the analog in one side, all the digital in the other side. And then they will make sure that none of the analog tracks are crossing the other side. And then they will not split it. So that also might work to some extent. So what I said is, so no currents are crossing the cuts. Means if your PCB, when you are designing, if your current need not be crossing both the areas, then you don't need any separating the planes. You know what I meant? For example, so this could be explained in two ways. One is between analog ground and digital current, digital ground, you are using an isolator, power supply isolator. So from the ground plane, from here to analog ground, because here you need some kind of return path, and then you got some power supply that is in the digital ground, digital plane, and then you got some filter, then you need a power supply for the analog. For that, if you are using an isolator here, and then that isolator is isolating the power planes, then you may not need actually the cut, because anyway you are isolating the top part. And then if you are putting all the currents here, means if you are routing all the currents is going through your routing here, if you are going through the routing, you may not need a split plane. So I will draw it and show you. So sometimes what people do is, see, they may have a simple system, not like your DSO. So what they do is, they may got some sensor, maybe a temperature sensor, and then they are using an amplifier, and then they are amplifying, then they got a filter, then they got ADC. Then what they do is, maybe they got a ADC, then they got a digital buffer or something like that, then they got some microcontroller, and then this signal is storing somewhere they are storing maybe an SRAM. So if this is a system, then you got analog, then you got digital, and then in this design sometimes they will not split it. What they will do is, here this is digital, fully digital, this is fully digital, this is fully digital. So then they will put all the digital here. So all the track here, all our digital track is here, and then all the analog track is here, and then this ADC, and then there is no track keys from analog is crossing to this side. You know what I meant? Only connection is happening through the ADC. So you don't have any track from here crossing to this region. All the tracks are confined here in the analog region, all the tracks here confined in the digital region, and the only connection happening is through the ADC. So in that case, even if you are not splitting, it will not, you don't need to split the ground plane. Here it is fine, even if you are not splitting, you are okay to some extent. But in your design, if you need, this is crossing to digital plane due to some reason, this signal is crossing to this part some reason, you know what I meant? If the design is getting complex, then you have to split your ground plane. If your connection is only through within the ADC, even without splitting, it is okay. Not great, but it will do your job unless you are using a very high resolution ADC. Then your pins might jump it. Otherwise, even without splitting also people design it. But I always recommend to split the ground plane. So whenever you have, so this is somebody, some less complex systems you will see without splitting, then you should not be surprised. It is possible, provided you don't have any extra copper track crossing from analog to digital. You know what I meant? If all the connections are through the ADC, then that is fine, even without splitting. But I personally split the ground plane. When we have ADC, especially it is a high resolution one, I am using so many analog ICs, so many digital ICs, I split the ground plane, and then I use an isolator or a necktie, because that is a good design. So that is the reason we are not following this convention of not splitting. In your case, it is not possible. In your case, you have connections between analog and digital, not through the ADC. You know what I meant? You got otherwise also connections. So in your case, you have to split it. But if there is no connection between analog and digital except through the ADC, then without splitting also it might be okay. So neckties. So necktie is a very important concept which we already discussed in the last lecture. Only one point we will be connecting. And then you already might be, already you finished the necktie design on Altium. And the net ties, if you take the PCB on the back side, you can see the net ties. Anyway, I showed you a much nicer PCB in the last lecture. Pay attention to where the current flows. So when is the deadline for your PCB? Do you know when is the deadline? This Friday, okay. So you got time. No, I thought that it's tomorrow or day after tomorrow, something like that. So, but then see, for DSO we have already covered the block level diagrams and the PCB design concepts and then front end, because we can't finish everything because we have to submit the PCB. I know that it will be ideal you submit your PCB in the end of the semester, but it is not possible. But we try, that's the reason I covered quickly front end, ADC, then PCB design, and still we need to learn PLL and all these things, but then we can't teach in the middle of the semester everything. So that is the reason we give you more marks so that you can catch up. And then plus I explained all the block level diagrams in my third lecture so that you know how to connect it. Why we need to get this PCB is because of the following reason. So please submit by Friday. We have to send your PCB to another company. They will send it to China for fabrication and then they will come back. And in China they have got excellent system. They will fabricate in 1 or 2 days. But then the postage and all the handling, even we order express, it will take time. So last year it was easy because last year we had a factory in Dandenong called PCB Fast. So we fabricated there. Still it took like more than a week. But then this year we don't have a PCB manufacturing company in Australia. So you have an opportunity, business opportunity. So we don't have a PCB manufacturing company in Australia. But problem is competitive. Your prices will be up here if you are making a company. So if you got some innovative way of making PCB for reduced price, then you can start a company because we don't have one in Australia. And then unfortunately our subject is the only subject that you need a PCB. You know that in other subjects you don't need a PCB. So that's the reason please submit by Friday, and then please make sure that you don't make many mistakes, and so that we get time to send it to China and then come back, and then then we already got all the components ordered. So that's the reason this subject coordination is a bit difficult because of the hardware involvement. So why I said this is so that you know that we are also putting a lot of effort to get everything done. We already contacted many companies because all the people are happy to fabricate, but then because we got large volume, some companies should agree that we have to fabricate in quick turnaround, like in a week time. Then suppose you made a big mistake in your PCB, what will you do? Still you can order somewhere and get it fabricated. So we will not reduce your marks. This is not an excuse for you to make mistakes. Suppose your PCB you made a big mistake, then the only way is you will lose a mark, but no. So I have decided that we will not reduce your mark. So but you have to fabricate somewhere else, like PCB Way is a company in China. They will give you like 4 days board in 4 days time. So if you make some mistake, don't worry, you can fabricate in another company and you can get it quickly, and then we will evaluate that one. Because if some mistake happened, then it is beyond your control if something happens. But that is not an excuse for not submitting or making mistake, because you have to pay some good money to get it fabricated quickly. Because this one is anyway you are not paying, is free. So that is it. So the summary is, please submit your PCBs by Friday, because then we get enough time to check and then send it. So when you design your PCB, pay attention to where the current flows. Many problems with mixed signal PCB, mixed means both analog and digital, can be avoided by following this simple advice. Pay attention to where the current flows. DC and low frequency flows mostly in the straight line path of least resistance between source and the load, and high frequency signals follow the path of least impedance, which is directly under the signal trace. In between frequencies flow by both paths, in between the two paths. The idea of using cuts to prevent the interaction between different circuits is most often unnecessary. Sorry, I think. Yeah, so pay attention to where the current flows. So many problem with the mixed signal PCB, mixed means analog and digital, can be avoided by this simple advice. Pay attention to where the current flows, which we already discussed. DC, which follows the straight line, path of least resistance, and AC, path of least impedance. And then you will like, what about the in-between frequencies? In-between frequencies flow by both the paths and in between the two paths. Then the idea of cuts to prevent the interaction between different circuits is most often unnecessary if your system is very simple system where you don't have any connection between analog and digital plane except through the ADC, then you may not need the cut. But as long as we wisely place components and route traces to prevent this from happening, like then you can manage without ground plane. But still I would place the cut wisely considering all the current flows. Means I would recommend when you have digital and analog, you need a split plane or you need to isolate, especially if your ADC resolution is very high. I will come to that point. What do you mean by ADC resolution? Then design guidelines for analog circuits. A few general rules concerning design of PCBs for analog circuits are: keep the signal path as short as possible. So your signal path should be as short as possible. This will help to minimize both voltage drops through the conductors, means that is your copper track, as well as electromagnetic interference by controlling loop areas in the ground plane. Provide separate analog and digital grounds and tie the two together only once using net tie. Provide one connection from the system ground to actual earth ground. Connect capacitive shields once to provide a return path to the noise sources. So these things are not relevant for you, but these are relevant for your DSO design. So then actual earth ground, there is one called earth ground or sometimes called a chassis ground. So that is, you might hear chassis. What do you mean by chassis? Because if you are designing a system and then you are putting in a box, a metallic box or aluminum container, aluminum box, and that is metallic, then the question is you need a earth, you know that one earth pin is there, means your system you are putting in a box and then that box will be grounded. Then we will not ground your signal ground directly with the earth. Then what you will do is use some kind of optocoupler, some kind of coupler is called optocoupler. We will study isolation techniques. So then we will use some kind of a coupling isolation technique. Both the ground will be connected using some IC. So because then it will not be contaminating the earth. So the best example is when you are, it's a satellite is again the big example. In the satellite, what will happen is your group will be designing one payload, maybe imaging camera in the satellite. Then you may be measuring the imaging camera, then the storage. From the storage, the data will be coming out. That's all your system. Then because this will come out somewhere and it will be going somewhere in the satellite. But then your box, then your camera is there. Then your camera will be not plastic. It will be metallic. Okay, because in the space you can't use plastic, so it's a pure, very good aluminum, maybe aluminum. And then the problem is this satellite got that your aluminum, then your system is within the aluminum. Then you got the aluminum, you got, that is a chassis, we call it the chassis. So that one got a ground. And then your system inside your signal PCB you got a ground. And then this chassis you can't make it floating. Then what you do is you use a grounding isolation technique. You might be using an optocoupler or some kind of isolation. We will study isolation techniques. So that will connect your signal ground to chassis ground. So it is not physically connecting a wire, it is isolation, but it's connected. So that is a earth ground. So analog with digital, separate ground planes, separate power supplies. See, we follow separate ground planes for the DSO because we got analog with digital. So your DSO is an example of a mixed signal design, mixed signal system. So when you go for an interview, somebody asks, what did you do? What is the exciting subject, some hardware? Then you can say DSO, we got a mixed signal because it got digital and analog. And then you can talk about separate planes, separate power supplies. We are using ferrite beads between the planes to avoid the noise. Then optocoupler or galvanically isolated digital control signals to reduce analog noise injection. So we will study about this kind of coupler. So that is for isolating two sides, two signals, both signal and ground. Design guidelines for analog circuits. A few general rules concerning design of PCBs for analog circuits. Metal should not be left electrically floating. So your metal should not be left electrically floating means you should not have anything that is open, because this will be a problem in high frequencies. What it means is you got designed the PCB, then you got some signal is coming that is not going anywhere. It come and end open-ended. You know what I meant? Means your signal is coming from some IC, it is not connecting anywhere. Simply one track is coming and ending. So that is called floating. So that is not good. In low frequencies, again, it will not be a problem. But in very high frequencies, this will be a problem, because the signal will see this as something else, some inductor. So we will study that later. So the metal should not be left electrically floating, especially the signal path. Maintain the balance of the system to prevent the common mode signals from becoming differential. Means your track, when you have differential line, you have to make sure that the lengths are matching, your length of the copper track. Limit the bandwidth of the system to the required signal bandwidth. Means when you have to design the system, you have to make sure that the bandwidth of the system to the required signal bandwidth. Means you don't need to have a big bandwidth for your design. When your signal bandwidth, your ADC, for example, for your DSO, your bandwidth is how much? We are using 40 mega samples per second. Then you don't need to follow 1 gigahertz design guidelines. You know what I meant? So that's what it says. Keep loop area small and always think as to where the current will flow. Again, loop areas is coming in the ground plane. So you have to keep in mind where the return signal is flowing. So your aim is something like this. So you have to keep the components, and then this is pretty much your DSO board. It should look like this after routing. So if you keep your components carefully, you get enough space, and then you don't need to worry about the space, and then you can accommodate even your innovative ideas. So then when it comes to innovative ideas, so you may have some innovative ideas, because if your DSO is working, if you answer the questions, you will get 40%. So the remaining 5% is for some kind of innovation. So when you make innovation, please make sure that your innovation is a self-standing design. So what do you mean by self-standing design? Suppose, so this please keep in mind, because your innovation should not damage your DSO. Because in the last year also I said the same, because in 2016 I have seen, so this is your PCB. Then if you are designing some innovative part, suppose you are making some innovative part to the trigger signal, then you make that part together, then this is your trigger part. This is an example. Then maybe put a 0 ohm resistance connecting these two. You know what I meant? Means from the trigger, this is going to here, and then this is going somewhere else to your system. So this is your innovation. So you made this innovative block that is connecting to trigger part, and then that is connecting to maybe ADC part. So then if that is your innovation, then make sure that the signal that is going to ADC, put a 0 ohm impedance here, 0 ohm resistance footprint. Here also 0 ohm impedance footprint. Means after soldering, you will not be connecting your innovation part to this DSO first. You will be testing and make sure that your DSO is working. If it is working, then you can short this two and then short this two, so that your innovation is introduced. Otherwise, what will happen is, I have seen previously, they messed up the DSO design because of the innovation went wrong. Then obviously if it went wrong, if you don't have the high frequency signals like 40 mega samples per second, what you can do is you need a knife and cut the track, then put the jumper, and somehow we can do something. But if it is high frequency lines, maybe it will not work properly. So if possible, maybe this will not be possible with your complex innovation, but at least you can reduce the risk by putting maybe a footprint of a 0 ohm resistance, and so that you can test your DSO working without your innovation part. Then when it is working, you can just introduce the DSO by shorting something. So that also is a good idea, so that you will make sure that your DSO design is not affected if something goes wrong with the innovation. So by the way, how many of you got some innovation in your design? Okay. Only one. No, so some people. Okay, good. So you should have some innovation. Without innovation, because I will come and ask you some question. If you have innovation, I will not ask you many questions because you already know innovation came. So I don't need to waste my time. So if you don't have innovation, I will ask you some questions. So please make sure that you have some innovation. So before going to the supply distribution, because supply distribution also we already discussed the supply distribution from another perspective. And maybe I will discuss about DAC because that part is important. So maybe a little bit discuss about supply distribution because again this one we already discussed the supply distribution. So in the supply distribution we will be talking about the bus topology. So what do you mean by bus topology? Bus topology means convenient but poor isolation of sub-circuits. Switching currents for second voltage fluctuation on supply rail means what it says is this bus, when you hear bus topology means you are getting power supply from somewhere and then that is distributing. So that is called the bus topology, BUS topology. Means you are getting a power supply and that power supply you are distributing to analog and digital or sensitive analog or switching digital. So when you have, it is not a good design. See, your analog and digital you are connecting together and then here you are providing, see here what will happen is these are the not real, this is not you have connected. So this resistance, this inductance, these are due to the copper track. These are again in the ground plane due to the copper track. And then if you do this type of bus topology, then you know what will happen. Your analog and digital are coupled together. So this is not a good topology, which we already discussed in the last lecture. So the best way is something like this. You will be isolating star topology. So then you are using, because you already know the concept now. I discussed it in the last lecture, but officially there are some names. So this is a simple bus topology. That is a distribution of power supply when you have analog and digital. So this is called star topology. So you are using star topology. What do you mean by star topology? Means you are not connecting these together, but instead you will be connecting separately, like from here, and then you are putting some isolation between these. Star supply distribution helps to isolate noise between circuit elements. Since supply lines are not shared, noise is not coupled. Means here what will happen is when this one is switching, lots of noise will come and directly go to the analog. From here return, directly go to the analog. So this is not a good design. And then here what happens is because of star topology, if we can put an inductor here, ferrite bead, then what is happening is then you are avoiding the noise coupling. Then here you will be maybe splitting the ground plane. So in the star topology, you can have split ground plane, then you can also isolate the noise. Then ground supply rail droop. So some people might say, what is a rail droop? What do you mean by that one? So conductors have finite non-zero resistance, and so current drawn through the ground supply lines or plane causes voltage variation between various points of the connection. So then this is the power supply. And then in the power supply, what is happening is the power supply it is going, and then this resistance is the resistance of your copper track. Resistance of the copper track, that is a ground plane. So in the ground plane, you got a common ground plane, then it doesn't mean that this one got 0 ohm impedance. Your copper track got some impedance, copper got some impedance. Then what will happen is you got a power supply. So this power supply, this is a ground plane. So this is a PCB, this plane, ground plane is this one. And then from here it's positive current it is taken from one IC. So you got one IC. The return current is 10 milliamps is coming to the ground. From another IC, return current 10 milliamps is coming here. From another IC, return 50 milliamps is coming, because all are coming to the ground plane. You know what I meant? So because here you got one IC, another IC, another IC, each IC is drawing different amount of current, then all the currents are coming to this ground plane. And then what will happen is here 10 milliamps, here 10 milliamps, here 50 milliamps, and then this point, then through this resistance, what will happen is how much current is flowing? 70 milliamps is going through this mole. So that's the reason in the ground plane, if you don't place your IC carefully, then you may get your ground will not be 0. It will be like 0.001 or something like that because of this issue. And then this resistance is coming. Why? Because your copper got a finite impedance, not 0 resistance. It got a small impedance value. So supply rail droop. 9 times out of 10 this is not an issue, but we can reduce the effects by using appropriate supply distribution topologies and PCB design. Means this ground shift because of this one is 9 times out of 10 is not an issue. You won't see that much effect. This will be applicable only when in your board when you have some high current stuff, then this ground droop will come. If you are milliamps current, this effect is very, very small. So when it comes is when you are having a very high current, like you got a regulator or something, or some LED drivers taking a lot of current, then you may see this one. Cases where issues with the droop arises include high current circuitry, which I already discussed, fine pitch supply wiring, supply voltage sensitive circuitry such as current sensing system. So when you have a current sensor, then the performance might affect if your ground plane is not at 0 volt. If you got a current sensing. Then power distribution issues, DC, R wire into IDC, means R wire, this is the impedance of your copper track, IDC is a DC current, and then that is called droop at the load. Then also you have resistive heating, you may have some heating effect because when the current, high current is going. Then reduce resistance with broader tracks and thick wire, you can reduce the resistance with a broader track. AC, wire impedance increases with frequency. When you have a copper track, then your impedance will increase with the frequency. AC current drawn by load translates to voltage fluctuations on the supply, which increases the frequency. Reduce the inductance with the broader tracks. Take home message. Supply rail voltages at a load are not rigidly fixed and may not be identical to given supply voltage, but instead depend on the network of distribution. Because sometimes what you will find is you may have a regulator and the regulator output is 5 volt, and then when you measure you will see only 4.98 volt. So there will be some voltage dropping, you might think where it is. It will be on your track if you put long lines. So poor bus topology. So as I said, why it is called poor bus topology? The shared return lines increases common current draw and therefore supply voltage drop to both the circuits. See, around 0.2 ohm, that is the around impedance of your copper. 0.2 ohm, not 0.2 ohm. So then this is a power supply. This you have got a power supply unit, maybe this is your regulator. Your regulator IC on the PCB is providing 5 volt and then this is a ground, 0 ground plane. In the circuit 1, here you got one IC and then your 5 volt you took it to this one and then you shorted to this IC2 and then ground you shorted together and then connected to this ground. Then what will happen is this requires 2 milliamps and then this requires only 0.2 milliamps. And there is an interconnect. This is a signal. So your signal is going from this IC to this IC, but then this is the way you connected your power supply. Then what will happen is from here how much current will come? 2 amps, 2.02 milliamps will be coming here and then 2 milliamps will be taken by this one, 0.02 milliamps will go here and then the return will come here, the return will come here and then the return here is how much? That is 2.02 milliamps will be flowing. And then if that is the case, 2.02 milliamps is on the ground plane, the current into 0.2. So that is how much it will come, around 0.4 volt. So your ground plane got 0.4 volt. Ground is not 0 because of this issue if you are shorting like this. But then what is a good strategy? The good strategy is let 5 volt connect to this one and then 0 volt connect to here. And then 5 volt connect here, 0 volt connect here. So this return path is only 2 milliamps, this return path is only 0.02 milliamps. So all got a separate return path. You are not allowing to add up the return path currents. So that is called a star topology. If the circuit is sensitive to supply droop, the separating the power supply lines would improve the system performance by reducing the droop width within 2. See, this is called a star topology. So digital systems. Digital systems are generally immune to noise on the supply lines as long as spike and ripple voltages do not exceed logic 1 or high. Digital systems are tolerant to power supply ripples but are affected by large supply transients such as spikes and supply droop due to burst of current drawn by ICs nearby. Means digital ICs are usually immune to the noise. As long as you may have some spike or some ripple voltages, and if it is not exceeding your logic 1, that is fine. So that is the reason digital is more immune, easy to handle. Then supply decoupling, which we already discussed. Load that draws fluctuating current produces voltage noise because of the switching, maybe digital, and then we will be using capacitors so that your circuit is closed here, or high frequency can be shorted to the ground. So this supply